Good day, ladies and gentlemen. Today I want to take you through the homework for graphing absolute value functions. Absolute value functions are equations that are most accurately described as piecewise linears. They're technically two linears being put together and meeting at a vertex. Each side of the linear equation is going to have an opposite slope of the other side. So if one were going up 1 and over 1, the other side would be going down 1 and over 1, and they would meet at a boundary where the vertex happens. Graphically, they have features just like a linear equation because each segment is a straight line. And they have features like a quadratic because there is a turning point or a vertex as well as an axis of symmetry. So you'll often hear me say that absolute value graphs are kind of like a quadratic and a linear had a baby. If you take some of the features of a linear and a quadratic and put them together, you often get an absolute value relationship. As an equation, you're going to know it's an absolute value relationship because you're going to see the absolute value bar. So that's going to make it very clear for you to understand that you are working with an absolute value function. Absolute value functions are identified as nonlinear because technically they don't make a straight line. Even though they have two segments that are straight lines, it's not one single line going on forever. And because they're nonlinear relationships, we're going to graph them from a table of values. All nonlinears are most often graphed from a table of values. If you take a look at the example down below, with the absolute value graph, we have similar features to a quadratic in some ways and to linears in others. Technically, absolute value graphs are piecewise linears, where two pieces meet at a vertex, and they often appear in vertex form, just like a quadratic. Because they often appear in vertex form, we can see or observe the vertex. If we take a look at the example question in the table down below, we might have noticed that we have, in vertex form, a relationship where A is positive 1, meaning that it's going up. We see the opposite of the horizontal shift, or where the vertex is happening on the x-axis, as well as the actual measured amount, what the y value is. So we notice that there's a vertex happening 1 unit of time from now at a measured amount of 3 for a relationship that is going up. In a table of values, at time 1, if we actually substituted 1 in place of x and evaluated that relationship appropriately, we'd end up determining that the measured amount is -3. What's fascinating about absolute value graphs, similar to quadratics, is that as you move 1 unit of time past the vertex and you evaluate that relationship, the absolute value of 2 minus 1 is positive 1, and when you subtract 3 from it, you get -2. If you evaluate the relationship 1 unit of time prior to the vertex, absolute value is always positive. So although technically you're doing 0 minus 1, because you're taking the absolute value of that difference, the absolute value of -1 is positive 1. And the expression ends up evaluating exactly the same as it would 1 unit of time after the vertex. So because you end up evaluating the same expression, you get the same measured amount. And that's why we have symmetry on both sides of the vertex in an absolute value graph. Absolute value is always positive. So at the times when it's supposed to evaluate to be a negative amount, it actually, -1 minus 1 should be -2, will evaluate to be positive, just like it would have when we had positive amounts on the opposite side of the vertex. So we get symmetry or sameness just like we do in quadratics. We get similar or identical measured amounts on either side of the vertex, which creates that repeated pattern, or that symmetrical or same pattern, and in this case the V pattern, because technically we're dealing with an x to the first power relationship. As we had mentioned above, technically absolute value graphs are piecewise linear functions. We could create an absolute value graph by taking one relationship and separating it into two pieces that meet at an appropriate boundary in time. It's a little bit tricky to do, but the bottom line is that if you have two linear segments, I know both of these segments are linear because they're both x to the first, and they have opposite slopes, the first relationship or expression has a slope of positive 1, and the second relationship has a slope of -1, it could be created in such a way that you'd have one segment going down 1 and over 1, down 1 and over 1, and it could meet at an appropriate time where it connects to the second segment at a boundary that goes up 1 and over 1. Technically, absolute value graphs are two linear segments with opposite slopes that meet at an appropriate point in time to form a vertex. We don't see that often, so it's not the most important detail, but it is good to know. Please turn the page. The next page should be page 67 in your packet. Page 67 was the first page of actual homework for investigating absolute value relationships. And because absolute value relationships are similar to quadratics, they often present themselves in vertex form. The cool thing about vertex form is we can see the vertex. So if you take a look at the first practice skill set, you're asked to identify the vertex as well as the axis of symmetry, which you should really do first, of each function, and compute the y-intercept. The cool thing about vertex form is you can see the vertex, but you do not get the y-intercept. So when we take a look at the first relationship, f sub 1 of x, you're supposed to know or immediately identify that as a quadratic because you notice that there's a quantity square. So it's just a second degree polynomial. It must be a quad. Because it's being presented to you in vertex form, we're going to label the numerical quantities, the coefficient of the group's quantity a, -1/5, or -1/5 is going to be labeled a, +5 is going to be labeled -h, and 8 is going to be labeled k. Because the coefficient of the squared term is -1/5, that tells us both that the relationship is going down and that it's going down slowly. 1/5 is slow. So it's going to open up and appear pretty wide. The axis of symmetry is the time when the vertex occurs in this relationship. And for this particular relationship, that is going to happen 5 units of time ago, because we're seeing the opposite of the horizontal shift, or the opposite of the time when the relationship occurred, when the vertex occurred. The actual vertex, as we had just determined, is happening 5 moments of time ago, or happened 5 moments of time ago, and it measured a maximum amount of 8. Because this relationship is going down, we should note the vertex is going to be the highest point, and 5 moments of time ago, the relationship measured 8. The only thing we don't see in vertex form is the value of the relationship at time 0, so that we would have to compute. We'd have to actually substitute 0 in place of x and determine the value of this at time 0. That can be done on your calculator, ladies and gentlemen, and it's always a good idea to reset it if you haven't done so already. Access to memory, choice 7, scroll to all, hit enter, and scroll down to reset. On my home screen, if I were to substitute in negative, the quantity 1/5, x plus 5, oh sorry, I didn't do that times 0, excuse me, 0 plus 5, and square it, I can determine that the value of this relationship at time 0 is in fact 3. So the y-intercept, or the value right now, is 3. And we can write that in one of two ways. We could either write f at time 0 is 3, or we could write 0, 3 as a coordinate value, indicating that the y-intercept of the value right now at time 0 is 3. If we go on to f of 2 and we do the same process, we label the numerical quantities a, negative h, and k. My hope is that the first thing you recognize is that we're dealing with a squared quantity, and because there's a squared quantity, that means this is going to be a quadratic relationship. In addition to that, I hope you recognize that a is positive 1, even though we don't see a coefficient for the squared quantity. We know that whenever there's no coefficient, it's automatically a 1. So because a is positive 1, this relationship should be going up. The axis of symmetry, the time when the vertex occurs, in this instance the minimum value, is going to happen the opposite of what we see added or subtracted to x. So it's actually going to happen 3.5 units of time from now. The vertex, we just determined, is going to happen 3.5 units of time from now, and it's actually going to measure exactly what we see added or subtracted to the entire expression, so it's going to measure negative 6. The only thing we don't get to see is the y-intercept, and the y-intercept is the value of the relationship at time 0, so that would have to be computed. We have to substitute 0 in place of x, and evaluate the expression on our calculator, or we could observe it in our table of values, which is the method I'll choose to do this time. If you wanted to observe this relationship on your calculator, you could go to your function list, you would substitute in the quantity x less 3.5 squared minus 6. Depending upon how the question is presented, students will sometimes choose to determine the value of the y-intercept just by going to their table of values. A lot of observations and computations can be observed in your table of values, and sometimes it saves some time. The y-intercept for this relationship happened at time measured 6 and 25/100 at time 0. You can take a minute and pause the video and see if you can identify the observations we just made in this quadratic relationship in vertex form on your own, and see how accurate you are with your interpretations. If you've done that, hopefully your work looks similar to mine. This is obviously quadratic because it is a squared quantity. The lead coefficient is negative 3. That's the amount being multiplied by the squared quantity, and that means this relationship is going down 3 times faster than normal, so it's going to appear really narrow. The axis of symmetry, the time when the vertex occurs, is appearing as the opposite of the amount being added or subtracted to x. So in this instance, it would be happening 1 unit of time from now. And the measured amount at that time will help us to determine the vertex, which is simply the amount being added or subtracted to the entire expression. The vertex is happening 1 unit of time from now when it measures a maximum of 9. The cool thing about vertex form is we can see the vertex, but the disadvantage is that you cannot observe the y-intercept value times 0. You'd have to compute that. So you'd have to evaluate the relationship at time 0 by substituting 0 in place of x, type that into your home screen, or look in your table of values and determine that it measures 6 at time 0. Therefore, the y-intercept is 0,6. As we move down the page, ladies and gentlemen, what you're supposed to come to know is that absolute value graphs are similar to quadratics, even though they have linear portions or characteristics to them. They're similar to quadratics because absolute value is always positive. So there will be times when the absolute value expression is supposed to have a negative quantity, but it won't, because we'll have to make it positive according to the rules of absolute value. Since that is the case, because we're making negative quantities positive, we're going to get a repeat in measured amounts. And because we get a repeat in measured amounts, we're going to see similar relationships in our graph as we do with our quadratics. We're going to see repeat measured amounts throughout time. If you take a look at g sub 2 of x, my hope is that when you observe that relationship, you're like, Tooch, check it out. There are these straight bar things for this expression, grouping x plus 3. That's going to mean we're dealing with an absolute value relationship. Because we're dealing with an absolute value relationship, that means our graph is going to make a V. Absolute value relationships appear to us in vertex form, so we want to label our numerical quantities A, negative h, and k. A is the coefficient of the absolute value quantity, and A is going to tell us if the relationship is increasing or decreasing and how fast. This one's going down half as quickly, so it's going to appear wide. In addition to that, the axis of symmetry, the time when the vertex occurs, the maximum or the minimum amount, is happening the opposite of what's being added or subtracted to x itself. So in this case, it happened 3 units of time ago. In addition to that, the vertex is going to happen at that precise time, or happened 3 moments time ago, with the actual amount being added or subtracted to the expression, 6. The only thing we don't get with vertex form is the value of the relationship at time 0. So that we'd have to either compute on our home screen by substituting 0 in place of x, or we could observe in our table of values by seeing what it measures at time 0. Let's give that a shot. Please go over to your calculator, and on calculator state gem and your function list, clear out whatever you have. Substitute in the quantity negative 1/2. I often like to put fractions into my calculator as grouped quantities rather than using the fraction cheat key. And in order to get your absolute value bars, you must go to Math, scroll to the second tab number. The very first choice, 1, is absolute value, and we need to put in x plus 3. Be sure to scroll out of your absolute value bars and add 6 or increase that expression by 6. If you graph the relationship, don't be surprised that it's going down rather slowly so it appears super wide. And when you investigate your table of values, if you wanted to graph this relationship, you would treat it like a quadratic. You'd want to get your first y value equal to your last, and that would require you to get symmetry or sameness throughout your table. As you scroll backward in time, what you'll notice is that you start to get some repeat measured amounts around 3 moments of time ago. And if you appropriately get your first y value to your last y value, you will set to the vertex. The vertex happened 3 moments of time ago at a measured amount of negative 6. If you observe the relationship at time 0, which was our initial intent, what you'll notice is that at time 0, this relationship measured 4.5. That's exactly what we would have gotten had we investigated or evaluated the expression at time 0. That is, through observation, the value of the y-intercept. So you could simply suggest at this point that this relationship at time 0 would measure 4.5. Or if you prefer, you could write that as 0, 4.5. Let's take a look at G sub 1 together, and then I'll give you a moment to pause the video and do G sub 3 on your own. In G sub 1, ladies and gentlemen, my hope is that the very first observation you make is that we have a quantity in straight bars, which indicates an absolute value relationship. And because absolute value is always positive, we're going to get repeat measured amounts, and that is going to create a V relationship on a graph, or a V picture. I hope you identify the lead coefficient as positive 1. Even though we don't see a coefficient or number in front of the absolute value quantity, technically when we have no coefficient, it's automatically a 1. So because the lead coefficient is positive 1, that means this relationship is going to be increasing at a rate of 1 at a time. It's going to be going up. As we work our way down the page, you should next identify the axis of symmetry, which is happening at the opposite of the amount added or subtracted directly to x. That is 2.5 units time ago. When we identify the vertex, we already know what the x quantity is going to be. It's negative 2.5. And we're actually seeing the precise measured amount at that time, which should actually be negative 8. This relationship 2.5 units time ago measured negative 8, which makes more sense because it was increasing. That value should be at the bottom. It should be a minimum amount. And then lastly, if you wanted to determine the value of the relationship at time 0, you'd have to substitute 0 in place of x, and on your home screen evaluate that expression. And I'll take a minute and show you what that looks like. If you went to your home screen, you'd have to get your absolute value bars in your math key. You'd scroll to number, select choice 1. You'd substitute 0 in place of x, add 2.5, scroll out of the absolute value bars, and subtract 8. And if you were to do that appropriately, you would see that this relationship at time 0 measures negative 5.5. If you were to evaluate G sub 1 at time 0 to determine the y-intercept, you'd have to substitute 0 in place of x, and when you type that expression into your home screen, it's going to compute the value as negative 5 and 5/10. You could write that in function notation, or as a coordinate value, you could suggest that at time 0 the relationship measures negative 5 and 5/10, and that's going to determine the y-intercept. If you have a moment, you can pause the video and make the similar observations for G sub 3 and see if you're on the right path, if your observations match the ones that we come up with together in just a moment. Before we actually make our algebraic observations, I'm going to take a moment and make some geometrically. Let's go to our calculator, and in our function list, if you have any expressions, please delete them out. Let's substitute in 6 and the absolute value expressions we get from, or bars we get from the math key. Scroll to the number tab and choice 1, hit enter. And we want to substitute in x less 2. Once we've done that, scroll out of the absolute value bars and subtract 8 from that quantity. To make observations, you could either look at the graph and see what's happening geometrically. It is in fact increasing. It seems to be happening rather quickly because the relationship appears pretty narrow. And when I go to my table of values, I get a lot of information. You're not always going to get the perfect ideal table to graph from, where the first y value is equal to the last, so you may have to scroll up and down in your table of values until that happens. There are many observations you can make in here that are incredibly important to confirm the work you just previously did. You should notice that if you got your first y value to equal your last y value, that you will have centered the vertex within your table of values. The axis symmetry is the time when the vertex occurs. In addition to that, you should be able to observe the y-intercept, the value at time 0. I hope that matches what you saw algebraically. Algebraically, the first thing you should have noticed was that there are straight bars in this expression, and therefore it's an absolute value graph, which is going to make a v. Beyond that, you should have noticed that a is positive 6, which means this relationship is going up 6 times faster and is going to appear pretty narrow. The axis symmetry is the time the vertex occurs, and it is always the opposite of the actual amount being added or subtracted to x. The horizontal, it's happening at the opposite of. The axis symmetry is always the opposite of the amount being added or subtracted to x. In this case, the opposite of -2 would be positive 2. 2 moments of time from now, this relationship is going to reach its minimum value. We already determined that the axis symmetry is the vertex is happening 2 moments of time from now, and the measured amount is the actual amount being added or subtracted to the expression, in this case -8. The cool thing about vertex forms, you can see the vertex, but you do not get the value of the y-intercept at time 0, so you'd have to compute that. And to compute the value at time 0, you'd substitute 0 in place of x, and I'll do that on my home screen of my calculator with you, second quit, so that you can see the actual expression being evaluated. 6, math, scroll to number, get your absolute value bars, type in 0 less 2, scroll out of the absolute value bars, and subtract 8. And you'll find out that at time 0 it measures 4, which is exactly what we observed in our table of values. If you were able to make a lot of those observations and or computations, we should be able to move on to the last question on the page. The last question on the page has us work with that previous relationship, and it wants you to graph it and make additional observations from both the graph and the table, in addition to the algebraic observations you made a moment ago. So based on what we saw a moment ago, we know that we have numerical quantities a, negative h, and k. We know that because we're working with an absolute value expression, it's going to graph to make a v. There's going to be repeat or symmetrical amounts throughout the relationship. We also know that the lead coefficient is going to indicate if the relationship is increasing or decreasing and how quickly. And since a is positive 6, this relationship is going to be going up rather quickly and appear pretty narrow. The axis symmetry tells us when the vertex occurs, the maximum or minimum amount. And we already determined that that is happening 2 units of time from now. And the vertex, we decided by observing the algebra, is happening 2 moments of time from now when the relationship measures -8. When you go to graph this, the most important thing to consider is that technically it's nonlinear because it doesn't make a perfect straight line. And nonlinears are most often graphed from a table of values. To set up a table of values, you just need a t-chart with x and g of x, which simply means y. To get the information for this table of values, you would go to your calculator as we did a moment ago. In your function list, in case you missed this a moment ago, I'll type it in again. You type in 6, math, scroll to number, absolute value bars, choice 1, substitute in x less 2, scroll out of your absolute value bars, and subtract 8. When you go to your table of values, if you do not have repeat measured amounts throughout the entire table and your first y value is not equal to your last, scroll up and down until you get that. That is the ideal table to graph an absolute value or a quadratic relationship from. As you copy these or transcribe these values into your t-chart, I would avoid copying down 3 moments of time ago, 2 moments of time ago, as well as 6 and 7 moments of time from now. They both have measured amounts that I can't fit in my graph anyway, so just to save a little bit of time, I would make the domain of my table go from 1 moment of time ago to 5 moments of time from now. As you copy down the x values that you intend on graphing in just a moment, you then must put in the appropriate y values. 1 moment of time ago, this relationship measured 10, it decreased to 4, down further to 2, all the way down to -8, then it began increasing and went back up to 2, back up to 4, and back up to 10. Once you have the appropriate data in your t-chart, the goal is then to plot that appropriately on your graph. When I plot information, I'm often in the habit of checking off the point as I plot it. 1 moment of time ago, this relationship measured positive 10. Right now, time 0, it is measuring 4. It goes down 1 moment of time from now to -2. 2 moments of time from now, it reaches its lowest value of -8. It bounces back up to -2 3 moments of time from now. It's symmetrical to the point 1 moment prior to the vertex. 4 moments of time from now, it bounces up to positive 4. And 3 moments of time from now, it's all the way up to positive 10. With a straight edge, preferably a ruler, and or the side of your calculator, or an appropriate mechanism, you can connect those points on either side and show this absolute value presentation. Once you've done that, we ask you a bunch of questions down below to see how well you understand what you just graphed and the information in the table of values. First, we want to know what are the coordinates of the vertex, which we already observed algebraically, but in our table of values, the vertex is going to occur as the middle of the table if you in fact got the ideal table to graph from, if you got your first y value equal to your last y value in the table. Graphically, the vertex will appear as the highest or lowest point on the graph, which we see as happening 2 moments time from now when it measures -8. That matches exactly what we were able to determine algebraically from the vertex form of our relationship. It is the lowest point on the graph, therefore it is a minimum value, and it also has the lowest measured amount in the table. -8 is the smallest measurement of all the measurements in the table, so we knew that that was going to be a minimum value. The equation for the axis symmetry allows us to know when the vertex occurs, and it's always equivalent to the x value of the vertex. So we could either look in our table of values and notice that at time 2 the relationship measured -8, or we could look on our graph and see that 2 moments time from now the relationship is at its lowest point. So the equation for the axis symmetry is x happens when x equals 2. They ask us to identify the interval where the zeros occur. The zeros are the roots of the x-intercepts. Roots are where a tree digs into the ground. That's where a relationship measures nothing. And for this particular relationship, it's interesting because their relationship doesn't intersect the x-axis at precise moments or integer values of time. It intersects the x-axis somewhere between time 0 and time 1, as well as time 3 and time 4. Those are the intervals that we want to write down in our response in just a moment. You may have observed that in your table of values because you may have said, Tooch, I happen to notice that from 0 to 1 moment of time from now, the relationship went from +4 to -2. And in between a positive and a negative lives 0. So it must have measured 0 somewhere in between time 0 and time 1. 0, 1, x, that's where this relationship is, or when it's going to measure 0. That happens again somewhere in between time 3 and time 4 by observing the table of values. I know that because at time 3 the relationship is negative, and at time 4 it went to positive. So therefore, in between a positive and a negative must have lived 0. Somewhere in between time 3 and time 4, this relationship must have measured 0. We'll have more precise ways of identifying that or computing that later on in the course. The relationship is concave up. It is increasing throughout time, and it appears as if it is curved upward. When we identify the y-intercept, we could have computed that algebraically above, as we did above, by substituting 0 in place of x. But since we have the table and the graph to support our work now, we could simply observe that at time 0 it measures 4 in our table of values, or we could have looked at the graph and looked at time 0 along the y-axis and notice that at time 0 it is in fact measuring 4. So whether we computed the y-intercept, observed in the table of values, or on the graph, we should know that the value of the relationship at time 0 is 4 through several different possible methods. When you're asked what interval is the relationship of the function increasing, we want to know as your eye reads the graph from left to right, when is it going up? As your eye reads the graph from left to right, my hope is that you notice that the graph is increasing from the vertex on into the future. So from the vertex on into the future, this graph is going up. Because we're able to make that observation, we should say that it's increasing from time 2 forward. The way that we say that mathematically is we say all values of x that are greater than 2, which must mean that it was decreasing for all values of x that were less than 2. As our eye read this graph from the past into the future, we should have noticed that it was going down up to the vertex, up to time 2. So for all values of x that were less than 2, the relationship was decreasing. When you're asked to determine the domain of the function, I usually write that on the bottom of the graph by identifying how much of the graph we used, and it appears as though we went from 1 moment of time ago to about 4 or 5 moments of time from now. But you have to be careful because there are arrow tips on this relationship, which means actually if our graph were bigger, this would have gone on forever. So technically we're going from negative infinity up to positive infinity in our observations. We can scroll up and down our table for as far as we want, and we would see predicted or observed measured amounts throughout all units of time. The range is a little bit different because as you identify how much of the y-axis you used, it only went down to -8, and it goes up forever because there's an arrow tip at the top. So the range goes from a low or a minimum of -8 all the way up to positive infinity if we were to scroll forward in time as far as we wanted to. The range can be expressed as either -8, positive infinity, all y values in between, Or the easiest way to write it is y is any amount greater than or equal to negative 8. There's two different ways you could have represented that. When you're asked to determine the value of the function at time 4, try not to confuse response or question K with question L. Question K wants to know what's the value relationship at time 4, and to do that you can simply go into your table of values and see what it measures at time 4. Or you could have gone onto your graph and had your eye travel over 4 units of time and up to the appropriate amount that the graph measures, which is in fact 4. So to determine the value of the relationship 4 units of time from now, you should say the value of the relationship 4 units of time from now is 4. That's a little bit different than L, which asks for what values does f of x equal 4. F of x, you're supposed to remember, simply means y. And I guess that should have said g of x, sorry. And this should have said g of 4. Oops, my bad. G of x just means y, and we want to know when does y equal 4, and that refers to the x value, or the units of time. We just determined that 4 moments of time from now it's going to measure 4, but what you need to know is that it also measured 4 at time 0. So there are 2 times that occurs. Your eye would have to observe that there are 2 times when the relationship is 4 units high, at time 0 and at time 4. So you'd have to either write f of 4 equals 4 and f of 0 equals 4, or you could write 4 comma 4, 0 comma 4, or you could simply write when x equals either 0 or 4, the relationship is going to measure 4. There's actually 3 presentations for that answer. When you're asked to determine how many roots there are for the relationship, that's the easiest question to finish off on. It just wants to know how many times it intersects the x-axis, and that happens twice. There are 2 roots. Ladies and gentlemen, this is the homework assigned to graphing absolute value relationships. And in order to graph absolute value relationships, it's important to understand that absolute value is represented with straight bars, and absolute value is always, always, always positive. So there's going to come some point in time where our measured amounts should have gone from either positive to negative, or from negative to positive, but they don't. They bounce back. They either go down and then come up, or go up and then come down. And because that happens, we get this repeat measured amounts and this symmetrical relationship similar to a quadratic. We don't simply get a straight line relationship. There are elements of the relationship that are like straight lines. We know that because we're dealing with an x to the power of 1, but the absolute value bars make that linear pattern bounce back and mirror itself on the opposite side. In absolute value relationships, it's important to understand that they are presented to us in vertex form. And the cool thing about vertex form is we can see the vertex. We label our coefficients or our numerical quantities a, negative, h, and k. The coefficient a tells us how quickly the relationship is increasing or decreasing, going up or down. H tells us the opposite of the time when the vertex is occurring. It's the axis symmetry. And k gives us the actual measured amount at that vertex. In order to graph absolute value relationships, since they are technically nonlinear, since they don't make one straight line, they should be graphed from a table of values. Most often, you're going to be using the ideal table to graph from, which for quadratics and absolute values will have our first y value equal to our last. That will center the vertex and allow us to see the most important point in the relationship. Hope that makes sense, and I'll see you all in class. Be well.